Hey everyone, so in the previous lecture we discussed how a stack is implemented, what are the various operations that can be performed over the stack, and in this lecture we will be discussing about applications of stack. Okay, so what are the applications that we have that can ease down the complexity of the algorithms or the problems that we're going to be discussing? Okay, so starting with why we are studying about these applications, because stack is a very important data structure when it comes to compilers, operating systems and algorithms. Okay, so understanding stack applications will be, you will be having a stronger base over how recursion works, how parsing is done. It can be language parsing that we discuss, like that we study in compilers, and how optimization problems are solved. And by optimization problems, it is like when you discuss operating systems, so there are various different techniques in which CPU schedules the processes. So stack plays an important role when it comes to optimizing the scheduling of these processes. Okay, so these are the common applications that are associated when it comes to stack. The first is function call management. So in functions and in recursions, you have like studied how recursion works and the importance of stack when it comes to calling these functions. Okay, undo redo operations that we have in the editor, backtracking, another important problem segment, which is backtracking. So we'll discuss more specifically backtracking later on in this course, but yeah, stack plays a vital role when it comes to backtracking. Then syntax parsing of these programming languages that these compilers use, and finally expression conversion and evaluation. So there are like three types of expression: infix, prefix and postfix. So these expressions are converted into one another, and stacks plays an important role in the conversion as well as evaluation of these expressions. Okay, so let's discuss them one by one, starting with the call stack. So what exactly a call stack is and how stack comes into the picture when it comes to function calls and recursions. Okay, so basically call stack is like a special area in memory allocated for subroutines. Allocated for subroutines. So subroutines, you can think of a subroutine as the different functions that are defined in the main function or the initial function. Okay, so these call stacks, what do we store in these call stacks? So these call stacks contain function arguments, local variable and the return addresses. So if it is not clear, then we'll be taking a example in order to make the understanding of how these subroutines are used and where stack comes into the picture to save us. And then we have recursion. Okay, and you already know what exactly a recursion is. A function is calling itself many times until a specific condition, which is the termination condition of the recursion, is reached. So stack plays a vital role when it comes to handle these recursions and subroutines. Okay, by storing the memory locations in this call stack. So let's see an example to understand how this exactly works, understanding the call stack. So here two functions are defined. The first is sub1 and the second is sub2. Okay, so line number 1, 2, 3 is the definition of the first function. Line 5, 6, 7 is the definition of the second function. And line number 9 is where the main function will first trigger the sub1 with value as 4. So the value of a will be 4. And here comes the importance of stack. So let us assume we have like the stack. Initially it was empty. I'm not considering that the first value of that stack will be the main function. Okay, let's assume that the initial value of the stack is empty. So now we are at line number 9 and it triggers this sub1 with value as 4. So In this stack, a block of memory which is at the top of the stack, initially the top will be 0, so a block of memory will be allocated, okay, and certain values will be stored in this block. What are the values? We discussed in the previous slide. The call stack contains function arguments, the arguments of the function with which this is called. Local variables, the variables which are defined locally in that function. And finally, the return address. So return address is the address of the location from which the function is called. Okay, so these are the main things that usually get stored in these call stacks. So here initially sub1 will be called at line number 9. Okay, so what are the, let's have 3 partition, one for arguments, second for the local variables, and third for the return address. Okay, so the first one, which is the argument, so the value of argument is 4, right? So value of a will be 4, value of a will be 4. Okay, then comes the second component, which is the local variable. So when we start the implementation of this, when the context is switched and actually sub1 with value 4 starts getting implemented, so we will see at line number 2 the value of b is 4. So b is the only local variable which is defined in sub1 and has the value 2. Okay, and finally the return address. Return address is the address from which the function is called, okay, from the parent function. So here the return address will be 9, right? When we have the value of sub1, we'll again return at like line number 9 and the function resumes, the main function resumes its operation. So return address will be return at line 9. Okay, so these are the 3 things on a broader way that this call stack usually stores. Alright, and this is the call stack for sub1 with value as 4, right? Okay, so what will be the output when you call this function sub1? The control will be transferred to this line number 2, value of b is 4, and it will return a plus b. A is the value of the argument, which is 4, and b is defined in this function, which is the local variable. So a plus b will be 4 plus 2, 6. So the value 6 will be returned at line number 9 at address this. Okay, so the value of this sub1 will be 9. Okay, so this will ensure that result 1, the value of result 1 is 9. Okay, so as soon as a specific function returns, we will immediately remove it from the call stack. It will be popped out. It will be popped out. And the control will be transferred to line number 10. Here will be the control. Okay, so line number 10 again calls another function which is sub2 with value as 7. So it will again allocate a memory block on the top of stack. So now stack is empty, and the new top will have again 3 values: arguments, local variables, and the return address. And this will be for sub2. This will be for sub2 with value as 7. Okay, so only one argument, which is c. So c will be having a value as 7, right? Now the next part, the local variables which are defined in this. So there is only one variable, but the value is not directly straight away given to us. In fact, another function which is sub1 is called at line number 6. Okay, so the value of d is unknown to us. The value of d is not known, right? Then again this sub2 calls sub1 from line number 6. So now the control is again transferred to sub1. So here in this sub2, the return address will be at this point. The return address will be the original one, which is 9. Why? Because this sub2 was called from the main function where at line number 10. So it has to be it has to return at line number 10, but this will not pop out the top of the stack. This won't get deleted. Why? Because it is still in progress, it is not yet completed. In fact, there is another function call which is sub2 happened at line number 6. So this will again create one more, this will again allocate one more block at the top of the stack, right? This is not yet popped. Why? Because it is still in progress. Why? Because value of d is unknown. So now the new top will be for sub 1 at line number 6. This is for sub 1 at line number 6, and it is, the argument is 7 here. So again it will be having 3 values or 3 partitions. First, for the arguments, here a is 7, a is 7, b is a constant which is 2, is the local variable, so b is 2, and the return address will be line number 6. This is where this sub 1 will return after computing the value which is a plus b, return at line number 6. Okay, so since this return will straight away execute, because we have a, we have b, the value will be 7 plus 2, 9. It will return 9, return at line 6, and it will return the value 9 to line number 6. So this will be popped out once it's over, or the return is executed basically. So it will be popped out, and the context is again transferred to the top of the stack, which is sub 2 at line number 10. Not line number 10, basically it will return over here. Then this line number 7 will execute. Again there is a return from this, and the context is transferred to the top of the stack, where we will put the return of the previous function to d, which is at line number 6. Okay, so sub 1c will return 9, therefore here d will become 9, and then we have return for sub 2, we have return for this function or this process. This will again return c plus d. We already have the value. It will update this d to 9, and then 9 plus 7, which is 16, is returned. So 16 is returned at line number 7, and this is finally popped out. This is finally popped out. And the value it will return, it will return 16, and the context will be transferred to line number 10, which is this. The value of sub 2 will be 16. So result 2 will be 16. So this is how call stack is used, and there is underlying data structure is stack in order to call these functions and store these call stacks. Okay. So let's see one more example in which we have a recursive function, and see how the call stack is used in order to get the value of this recursive function when the function is calling itself again and again. So this is also the same thing. It's just the same function will get called, and you will store the call stack on the top of the previous call. That's it in the stack. So again, the process remains the same. Define a stack and store these 3 values, which is in every call stack. Initially the stack will be empty. So it will, the line number 7 will be executed in the beginning with argument as 4. So this will be called, this factorial will be called. So the first function call, assuming that we are ignoring the main function for just for understanding. So this first factorial call will have the argument as 4. This is factorial 4. Okay. Now any local variable? The answer is no. There's no local variable defined in this. So let's have it empty. So it will first check if n is 0 or not. It's not. So else part will get executed. So this again the context is transferred to one more factorial is called, but in the first call stack the return will be at line number 7. So return at line 7. Okay, but here at line number 5 it will call factorial n-1 again. So since the initial factorial function is not yet completed, so it will remain in the stack and one more call stack will be stored on the top of stack, okay, with factorial with argument as n-1, which is 3. So again the value of n will be 4. So empty will the local variable will be empty, no local variable, and it will return at line number 5. It will return at line number 5. But since this also do not have the value of n is not 0 in this case as well, it will again call, the else part will execute, and this again call the same factorial function. So we won't be popping anything from the stack and the context will be transferred. So one more element will be added or pushed on top of the stack with value as 2. So n becomes 2. It will be, it won't be 4, it will be 3. Yeah. This will be empty, no local variable, and it will return to line 5. Return to line 5. Why? Because it is called at line 5. Okay. Again, one more function call with factorial as 1. One more function call with factorial as 1. Again, n is not 0. Line number 5. So n will be 1. Empty, the local, no local variable. And again it will return to line 5. Okay, so it will again trigger the final factorial with value of n as 0. Factorial with value as 0. So n will be 0, no local variable, and finally this if will get executed. The control will be at line number 2. Value of n is 0, so it will return value as 1. It will return the value as 1. And where it will return? It will return to line 5. It will return to line 5, and what it will return? It will return the value as 1. It will return the value as 1. And this is popped. This is popped. And where will be the control? The control will be at line 5. Control will be at line 5. This factorial. For this case, when you are in this call stack, the value of factorial 1. The value of factorial, not 1, value of factorial 0. Because we want the value factorial as n-1. N is 1 in this case. So we want the value of factorial 0. The value of factorial 0 is returned from this is 1. Value of factorial 0 is 1. So n times 1 can be calculated. N is also 1. The value of factorial 0 is also 1. So again it will return value as 1. So this will be popped. This will be popped. And it will return value as 1 to this function or this call stack. Okay, at line number 5, the value of factorial 1 will come from here, which is 1. Okay, So we have value as 1, n is 2, n times factorial 1 would be 2. So this now will return value as 2 of factorial 2. Okay, and we will pop it. The context will be at line number 5, the value will be 2. The context will be at line number 5, the value of n here is 3, so it will be 3 times 2. The value is 6. It will return value as 6 of factorial 3, right? And this will be popped from stack. Why? Because there is nothing more which is pending in this function. So it will be, we'll pop it from the call stack. Okay, and finally this will return the context at line number 7, which is this. This will return the context, no, not, it will return the context at line number 5, which is 3, in order to finally calculate the value of factorial 4. So value of factorial 4, or the value which will be returned over here, will be n is 4 times factorial 3. It will be 4 times factorial 3, which is returned from the previous call stack, 6, which is 24. So when we pop the final value which is present in the call stack on the top of the stack, it will return value as 24 at line number 7. This is where 24 will be returned. Okay, so this is how you will be going forward, or you will be simplifying these sort of recursive functions using a stack. Okay, so you have to remember that you need to store formal arguments, like arguments, the local variables, and the return address. And if the function is still in progress, then you do not have to pop it out. Just calculate what exactly we have to simplify if the function is not yet completed. That's it. Okay, so this is how recursive functions, like stacks, are used in these function calls. Okay, it's call stack for recursion. So let's see one more illustration in which we need to give the output of the following code snippet. So given the code, it has two functions, function A and function B, and function A is called with argument as 3. Okay, so let's create a call stack for this code snippet. Okay, so initially the stack will be empty and function A with value 3 will be called at line number 13. Okay, so function A with value as 3, the value of argument, which is n, in this case will be 3, right? Then if n is greater than 0, which is true, it will print A as 3. So this is the output. So it will first print A, value of n, which is 3 in this. Then it will call function B with value as n minus 1 at line number 4. Okay, and this function A is still executing. It is still executing, and the context will be passed after it finishes at line number 13. So it should return at line 13. Okay, but somewhere in between line number 4, it triggers another function. So there will be one more element on the top of this stack with value as n minus 1. N was 3, so it will be called with value 2. So here n will be 2, n is greater than 0, it will print B as 2. So it will print B, value of n will be 2 because it is printed in this function call when n is 2. And again at line number 10, it calls function a with value n minus 2, calls function a with value n minus 2. But first we need to mention where this function b will return. It should return at line number 4. Okay, and still there is one more line, which is 11 needs to be executed, so we won't be popping out this one from the stack. Okay, so now again this will execute function a with value as n minus 2. N is 2, so function a with value n minus 2 is 0. 2 minus 2, 0. If n is greater than 0, which is not in this case, here n is 0. So if n is not, so there is no else part, so this won't be executing, and we will straight away, it will return at line number 10. It will return at line number 10. It won't print anything. We simply pop it out at line 10. So this function a will not print anything because this is not satisfied. N is not greater than 0. Okay. So after line number 10, line number 11 will get executed. It will print b done. It will print b done, and the value of n would be, in this case, 2. Value of n will be 2. So you have to be very careful and printing the values in a specific function call. Okay, so that's why in this call stack you need to maintain all the values, all the parameters, all the local variables which are defined in that function call. So it will be 2, right? And control is again transferred. So once this is executed, it will be returned and this will be popped. We will pop and we will return to line number 4. Okay, what is line number 4 here? So the next line that will get executed is line number 5. Print a done with value of n in this. Here value of n is 3. It will be a done, value as 3. Okay, so line number 5 is the last statement of function a. So it's time to pop it out and return to line number 13. Line number 13 is it is not printing anything, so we'll just return from the main function. So this is what the output of this code snippet will be. So this is the way you have to deal with these subroutines or these recursive functions and use stack in order to get the output or to understand the behavior, what exactly the code snippet is doing over here. All right. So the next application of the stack, which is undo and redo operation. Okay, so like all of you have used these operations, and the shortcuts are Control Z for undo, Control Y for redo. So undo is basically the undone of the last operation that you have did, and redo is just opposite of that. Okay, so if somehow we able to store the operations that we are performing in the stack, then undone is basically popping out the last action, which is popping out the topmost element which is present in the stack. Okay, because that action will be the last action that we did on the in a specific application. Okay, so undone is basically popping the last action, and redo is use another stack to restore the popped actions. Okay, that's why let's have an example for a very simple case of typing. Okay, so initially we are in an editor. So we have an stack keeping all the operations that we are performing in that editor. Let's assume that letter A was typed in the beginning. So the action add character A was added to the stack. Okay. So at this point, at this specific point, if you try to press Control plus Z, you want to undo this action. So initially the stack was empty, and this operational stack, let's call it operational stack. Basically a stack having all the operations in the order in which they are occurring. Okay. So at this instant, when you just typed letter A, the operational stack has the operation add A, okay, and A is added in the on the screen. So if you type Control Z, this is just same as popping out the last action which is present in this operational stack, which is add A. So at this point, undone is equivalent to pop the last action, which is add A. So we'll remove this add A, and the undone effect will be the removal of A, just opposite of the action which is present in this operation. That's it. Okay. So then let's assume we added another character B and then one more character as C. So the operational stack, assuming that you undo it and redo again, okay, add A, add B, and then add C. So it will be having add operation A, then add character B, and then add character C, okay, and the value that you see on the screen will be A, B, C. Okay, you type 3 characters. So these 3 actions have added 3 elements in the operational stack: add A, add B, and add C. So now you go and redo this. Okay, now you go and redo this. So basically, to redo it, you need to maintain another stack to restore popped action. Okay, you need to maintain another stack to restore the popped actions. So let's assume you have one more stack. Why one more stack? Because the redo is basically the inverse operation, the inverse order of the operation that are performed by the user. Okay. So let's assume you undo for the first time. You typed Control Z, it will pop the last action. In this case, at this instant, the last action is addition of C. So this will be popped out. This will be popped out. The resulting string will be A, B. C is already popped out. So C will be removed. Okay. Then you perform another action, the second undo. Again you pressed Control plus Z. This will again pop the topmost element. It will pop this. B will be removed and we only left with A. And these undo operations, so in order to maintain the order in which we are undoing or we are performing any action, these undo operations are stored in another stack, which is the redo stack. So every undone operation is stored in this. The first one is add C, then it was add B. Okay, why stack? Because the order is also important. After 2 undo operations, if you perform a redo, in that case the element B will be added, not C. Therefore, a stack is used in order to maintain the order in which we are undoing. We need to find a order which is reverse of the order in which we are performing the undo operation. The last undo was add C, then there was one more undo operation to add B. So if at this point we try to perform a redo operation, which is just make an opposite operation of the last undo. The last undo was to remove B, so it will add B. which is popping out the top element of the redo stack. So if you perform redo at this instant, it will add B. Add B is simply to pop out the first element of this redo stack. Okay, this pop will add B. So now value will be A, B. Okay, so at this point, so the next step in this example is say redo 2. So redo 2 will simply remove the topmost element in the redo stack and does this operation, which is add C. The string will be ABC. But what if at this point you try to undo one more? You try one more undo operation. So that undo operation will basically undo the last redo. Okay. So the next operation will be the second redo. So what it will do is will pop out the top element from the redo stack and then update the text to add C. It will return C and ABC again will be visible on the screen. Okay. So just for a minute, just forget about this redo operation. What if you only have this undo operation? What if you only have this undo operation? So by the name, you can have a sense that it is undoing the operations in the reverse order in which they are done for the first place. Okay, and wherever these this similar operations are required, so stack always comes into the picture. So here comes the advantage of stack. So the order in which you pop out the elements from the stack is in fact the reverse of the order in which they are added on the first place. So wherever this specific scenario is required, you will always use stack. Okay, just keep this in mind. So here comes one more application of stack which are widely used in compilers, and this there are multiple use cases. A specific case I have taken, which is balanced parenthesis. So stack is can be used in order to find whether the parentheses are balanced in a given string or not. Okay, so it's a very simple application, but compilers use a very complex applications of these stacks. So let's see how you can figure it out whether the given string has the parenthesis in balanced form or not. Okay, so stack can be used in balancing, in checking whether it's balanced or not. Let's assume the first case number 1, starting with the empty stack. Okay, and the rule is simple. Whenever you see a opening parenthesis, just add that element in that stack, and whenever you see the closing parenthesis, pop out the element from that stack, which is the topmost element, and then compare whether the current string is balancing the element which is popped from the stack or not. If everything runs smoothly, everything perfectly balances, in that case the string is balanced, otherwise it's not. Okay, so starting with this, so the string is like this. The string is the first curly brace, then it's a square, then parenthesis starting, then closing parenthesis, then closed square bracket and closed curly. Okay, so starting at this place, it's the opening parenthesis. So we'll push it in stack. Okay, then you move +1, then it's opening square bracket, we push it in stack, +1, opening curly braces, push it in stack, +1. Now it's a closing parenthesis. So what the rule says, so if you find any specific form of a bracket which is getting closed, just pop out the element. So we'll pop it out. So pop will return this, and then compare it with the given closed parenthesis whether it is balancing out or not. So this is perfectly balancing, so it's like all good, +1. Then it's closing square bracket, the next element to be popped will be this. Again, this is also balancing out, all good. And finally, we'll pop the last one, and this is also perfectly balanced out. So after completing the traversal of this given string, after completing the traversal, just check whether the stack is empty or not. If s.top, if stack.top is equal to 0, then the strings are balanced. Otherwise, not balanced. Okay, got it? So let's see the second example now. So what is the string? So let me have the B part over here. So the string is opening curly brace, then opening parenthesis, opening square bracket, closed parenthesis, closed square bracket, and closed curly brace. So we can like easily see it. Logically, it is not a balanced parenthesis, but yeah, we can use stack in order to find it out. Okay, so starting from this, we push it, then we'll check the next one. It's again opening, we'll push it. Again the next one, it's opening square, we will push it. Then it's opening parenthesis, like it's closed parenthesis. So whenever you see a closed bracket, we just pop out the element. It's the square, it's opening square bracket, so it is not matching with the current string. It's not matching with the current string. So as soon as you get a unmatched scenario, just return saying not matched. Okay, you no need to check further. Why? Because we already find an instance in which the brackets are not matching. Okay, so no need to like complete the traversal in order to reach the situation where the stack top is not empty, and then this will like anyway execute. After returning, we'll check s.top. If it is 0, then balanced. Not, so it is not balanced. Okay, so just hold the execution and return. So we'll see the code of balanced parenthesis and the demo. Now let's see some stack applications that we discussed in this lecture. So let's implement the balanced parenthesis, right? So given a string, some parentheses in that string, so whether the string is having them in balanced form or not, let's see how we can do it using stack, right? So let's define a function called isBalanced, which takes a string as an argument, right? So a stack will be required in order to check whether the parentheses present in this string are balanced or not. So let's define an empty list. We'll use it as a stack. Okay, so what will be the idea? The idea will be initially the stack is empty. And a string is passed to this stack, right? So let's assume, let's have a understanding where the string is very basic, just a open and a closed parenthesis, right? So what the algorithm will do is, so whenever we encounter, we will traverse the string character by character, right? So we will traverse the string character by character. In this case, first character is open parenthesis and second is the closed parenthesis, right? This is index 0, 1. So we will first see the first character of the string, which is the open parenthesis. Whenever we encounter an open parenthesis, we will push that into the stack, right? So for index 0, we encounter open parenthesis, so it will be added to the stack, right? correct? Then we'll increment the counter to see the next character. So we will traverse it character by character until the string gets exhausted, right? So idea is whenever we encounter open parenthesis, push it in the stack. So open parenthesis, push, closed parenthesis, pop. That's it. Push and pop in this fashion. And once we have checked all the characters in the string, we'll just check what is the length of the stack or the array, right? If the length is empty, in that case the parentheses are balanced. If the length is non-empty or non-zero, in that case they are not balanced. For instance, if we see this string, open, 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 closed and closed, if this is the string, what will be the course of actions of this algorithm? It will be, there are 5 characters present and initially the stack will be empty, right? So the idea is every open parenthesis will push that parenthesis in the stack. So first there will be a push, the stack will be like this, then again push, again one more open parenthesis, then again push, 3 open parentheses, then there is a closed parenthesis. So this closed parenthesis will ensure that the last open parenthesis that we have added or pushed in the stack should get removed. So this will pop this out. This will pop this out. Then again a open parenthesis, we will pop again. And finally, if there are no further closed parentheses present in the string, in that case there will definitely be few open parentheses present in the stack. So stack is not empty. Stack will not be empty. And we can directly check by the length function, length of the stack. If it is 0, in that case it's empty and it's balanced. Or else if it is not 0, then the parentheses are not balanced. So this is how we will be checking the balanced parentheses using the stack. Okay, so let's quickly see the code. All right, we defined an empty stack, right? The idea is we will traverse the string str character by character. So a loop is required for character in str, and this character keyword or variable will give me character one by one sequentially starting from the first one. So if, let me use a smaller variable name, if char is equal to, and in this function I am assuming that the string only contains the curly braces. The assumption is str will be like this. That's it. Right? So if we encounter a open parenthesis, the idea is just add that element to the top of the stack, which is appending this character to the stack. So stack dot append this character, right? Else, to be more precise, what if the character is the closed parenthesis? In that case, stack dot pop, it will remove the topmost element or the last inserted element from the stack. And finally, once we are done with the traversal, we will just check the length of the stack. If the length is 0, in that case return true or else return false. So this will automatically do the job for us. So it will be true if is 0 or stack is empty, else false, right? So now let's see, by giving few strings to this function is balanced. Okay, So let's give 3 open parentheses and 3 closed parentheses. It is true, right? Why? Because there is open, open, open and 3 closed, right? Now let's change the order, or like remove any one of them, or try it with some other combination. Yeah, in this case, the second one, I have removed the last closed parenthesis, so it should return false for this instance of the str. And in the last one, I have just like rearranged 4 open and 4 closed parentheses. So it is working fine, right? The second one is not balanced. There are 3 open parentheses, but only 2 of them are closed. So that's why the second one is non-balanced string. So this example can be treated as the application of stack when where we can check the parentheses are balanced or not, right? So now I have a homework for you. Update the is balanced function such that it can check for balanced parentheses involving other parentheses as well, involving curly braces, involving square braces and parentheses, involving these all. Okay, so think about it. It is not that difficult. Only a slight modification would do the job, and we do not have to tweak this function drastically in order to achieve the homework problem. Now there is an issue with this algorithm. Now, pause the video and think about what is wrong with this. So what if I provide the input like this? What if I provide the input like this? Yeah. So there are 2 open, 2 closed first and then 1 open. So this, for this scenario, the algorithm will fail. Think about it why. Alright. So here is a pop operation involved in the stack. So what if the stack is empty? There might be instance for this case, initially the stack is empty. So we encounter the first character, which was the closing parenthesis. So here the pop operation will fail. So to fix it, before removing the element from the stack, we should always check whether the stack is empty or not. In case the stack is non-empty, then only we should pop it out. If it is empty, in that case, even after in an empty stack, we are encountering a open parenthesis or a closed parenthesis. That means they are not balanced, right? Okay, so if not stack, this is the check when the stack is non-empty. When the stack is empty, it will be true. Then just return false. So if it is not returning false in this line, that means there are some elements present in the stack and pop will not fail. Okay. So let's see. It's working perfectly fine. So always do remember, whenever you encounter pop operation, do check for the underflow condition. So this is the underflow check in this problem.